Let's now take a look at hydraulic systems. Hydraulic systems are ideally suited to provide a strong linear motion. The system uses a fluid, a light grade oil, to transfer energy from a pump to an actuator. A simplified system consists of the following components: a tank of hydraulic fluid, a pump, a control valve, and a cylinder. The pump pushes the fluid through a tube to a control valve. The control valve directs the fluid to the cylinder, causing the piston to move down in response to the fluid pressure. The pump is the actual source of mechanical power, and it is physically separate from the cylinder actuator. The practical significance of this fact is that only the cylinder needs to be mounted at the place where the motion is needed. The pump can be elsewhere. This allows a relatively small component, such as a hydraulic cylinder, to provide far more power than a similarly sized electric actuator, which must have the motor attached. Liquids, including hydraulic fluid, are incompressible, which means you can't compress them. Each 1 cubic inch of fluid pumped into the system must appear somewhere else down the stream as 1 cubic inches of fluid volume. Pascal's principle states that a fluid under hydrostatic pressure will exert the same pressure uniformly on the inside walls of all the interconnected components. The unit of pressure for SI units is the Pascal, PA, where 1 PA is 1 Newton per meter squared. 1000 PA equals 1 kPa, which is a much more useful unit of measure, and 1 pound per square inch, or 1 psi, is equal to 6,89 kPa. In this chapter, the pressure values referred to are technically called gauge pressure, meaning that the pressure is above the ambient pressure of 100 kPa. The principle of hydrostatic pressure is illustrated, which shows a tank, pump, piston, and hydraulic cylinder. The fluid on the high pressure side of the pump is measured at 100 psi. This means that the tubing, cylinder walls, and piston are all receiving 100 pounds of force for each square inch of area, as indicated by the arrows. All internal surfaces are under pressure, but only the piston is movable, so it moves to the right. The force on the piston from the hydrostatic pressure is the product of the pressure times the area of the piston face, as is given by the following equation. F is equal to P times A, which is equation 10.1 in your text, where F is the total force exerted on the piston, P is the hydrostatic pressure, and A is the area of the piston face. Let's look at an example. The hydraulic cylinder in figure 10.11 is 8 centimeters in diameter. Find the force exerted on the piston if the pressure is 700 kPa. We can use equation 10.1 from the previous slide to find the force, but first we need to find the area of the piston face. So we know area is equal to pi r squared, and that's r, not d. So the diameter is 8 centimeters. Make sure you convert that to the radius. So pi times 4 centimeters squared gives you 50 centimeters squared. Now we can calculate the piston force using equation 10.1, knowing that the pressure is 700 kPa, which is 700,000 newtons per square meter. And so the force is equal to pressure times area, or 3,500 newtons. Static hydraulic systems can be used to amplify a force. This is the principle used in hydraulic jacks or hydraulic brake systems, and is illustrated. The system contains two cylinders of different diameters that are connected by a tube. When a force is applied to the small piston, a pressure develops. This pressure is transmitted through the tube and is applied to the large piston. Because the large piston has more surface area, it receives a larger net force. Of course, it is also true that the large piston will move a shorter distance than the small piston because the work done by the two pistons must be the same. Let's look at an example. The small piston has a face of 2 square inches and receives an external force of about 10 pounds. The large piston has a face area of 20 square inches. Calculate the force exerted by the large piston. The small piston has a surface area of 2 square inches and is being pushed with a force of 10 pounds. Rearranging the equation 10.1, which is F equals to PA, and solving for P, we can calculate the fluid pressure this will create to be 5 pounds per square inch. The pressure of 5 psi is conveyed to the larger cylinder where it pushes on a 20 square inch piston. Rearranging equation 10.1 again, we can calculate the force on the larger piston of 100 pounds. Thus, the large piston will exert a force 10 times larger, but will move only 1/10 of the distance of the smaller piston because the volume change must be the same for both sides. You can check this by recalling your physics and the equation. Work, normally measured in joules or Newton meters, is equal to force newtons times distance in meters. In an active hydraulic system, a pump is used to create the hydrostatic pressure. A common pump design, called a gear pump, is shown, which consists of 2 meshed gears in a housing. As the gears rotate, fluid is trapped in the little spaces between the teeth and the housing, both top and bottom, and is conveyed from the inlet to the outlet. The mesh between the gears in the center is tight enough so that no fluid moves through either way at that point. This type of pump is known as a positive displacement pump because a constant volume of fluid is pumped for every revolution of the gears. The vane pump is another type of hydraulic pump. It consists of an offset rotor and a housing with retractable vanes. The spring-loaded vanes push out and seal against the housing wall. Because there is more fluid between the vanes in the top half of the housing than in the bottom, there is a net transfer of fluid from the inlet to the outlet. In some designs, the position of the rotor axis is adjustable. The more offset the rotor axis, the more fluid is pumped. Such a pump is called a variable displacement pump. A third kind of pump is an axial piston pump. It uses small pistons reciprocating back and forth to pump the fluid. As shown, the pump consists of a rotating cylinder and a metal ring called a swash plate, which does not rotate. The cylinder contains a number of small pistons that do the actual pumping. One end of each piston rides against the swash plate. Because the swash plate is at an angle to the cylinder, each piston is forced to move in and out with each rotation of the cylinder. By changing the angle of the swash plate, the quantity of fluid pumped per revolution is changed. The most common type of hydraulic actuator is the hydraulic cylinder. A typical cylinder is shown in Figure A and is known as a double-acting cylinder because it can provide force in either direction. It consists of a piston and a cylinder body. The piston has a rod that extends out one end of the cylinder. Fluid can enter and leave the cylinder on either side of the piston through ports. Under normal operating conditions, both ends of the cylinder are filled with fluid. If additional fluid enters port A, the piston will move toward the right, but the fluid must be able to escape through port B. A selection of hydraulic cylinders is shown in Figure C. Some hydraulic actuators can create rotary motion and are very similar to the pump designs discussed previously. For example, the gear motor rotary actuator shown is almost identical to the gear pump. For the motor, fluid is pumped in the left side of the case, putting the area under pressure, indicated by the small p's in the diagram. Within the pressurized area, all surfaces receive a force, but only those three surfaces indicated with the arrows will affect rotation. The other surfaces are balanced out or unmovable. The pressure on the teeth next to the case, top and bottom arrows, will cause the gears to rotate as shown. The pressure on the meshing teeth in the center would cause the gear to turn in the opposite direction, but this torque is overpowered because two teeth, top and bottom, are pushing the other way. A pressure control valve is a spring-loaded valve that is capable of maintaining a constant pressure in a system regardless of the flow rate. This is important because most pumps, such as the gear pump, are a constant displacement type. A constant volume of fluid is pumped for each revolution of the pump shaft. If the pump were connected directly to the cylinder, it would have to start and stop each time the piston is moved to a new position. Such on-off cycling reduces the lifetime of machinery and is therefore undesirable. When a pressure control valve is put in the system, the pump can remain on the whole time. When the fluid pressure exceeds the preset limit, the valve opens and the surplus fluid is simply returned to the tank. In other words, when the piston is not moving, the fluid is simply circulating from the tank, through the pump, through the valve, and back to the tank. If the pressure control valve opens at 1000 psi, then the pressure in the lines will never get much above 1000 psi. This diagram shows the inside of a simple pressure control valve. Notice that the passage from the pump to the load is always open. If the hydraulic pressure in the main passage overcomes the spring pressure, the valve opens and the fluid can escape out of a separate port that is connected back to the tank. The pressure at which the valve opens can be set by adjusting the tension on the spring. An accumulator, which is connected to the system, is a special kind of spring-loaded storage tank for hydraulic fluid. The accumulator serves two functions. First, it acts like a low-pass filter to remove pressure pulsations from the pump. Second, it stores extra fluid for those high demand times when the actuator requires fluid at a faster rate than the pump can supply. This latter situation is illustrated, which shows a pump with a capacity of 1 gallon per minute supplying fluid to a cylinder. Notice that the accumulator is located between the pump and the cylinder. In Figure A, the valve to the cylinder is closed. Consequently, all fluid from the pump goes into the accumulator, compressing the accumulator spring. In Figure B, the valve opens enough to allow the fluid to the cylinder at a rate of 2 gallons per minute. Because the pump can supply only 1 gallon per minute, the other 1 gallon per minute comes from the stored fluid in the accumulator, which is pushed out by the spring. Naturally, this concept will work only if the cylinder's demand for fluid is intermittent, but this is often the case. In fact, this is one of the advantages of a hydraulic system. It can store energy within the system to be used during periods of peak demand. For example, consider the case where a robot performs a 10-second lifting operation, which requires 1 horsepower once each minute. Because the average load is only 1/6 of a horsepower, which is 1 horsepower times 10 seconds divided by 60 seconds per minute, a hydraulic system could get by with a 1/6 horsepower pump. For 50 seconds out of each minute, the pump would be charging up the accumulator. For 10 seconds, both the pump and the actuator would be supplying the cylinder. Now, suppose instead of the hydraulic system, the robot used an electric linear actuator. Because the electric motor cannot store up energy, it would have to be a full 1 horsepower, even though it is only on 1/6 of the time. There are 3 types of accumulators: spring-loaded, which we've already mentioned, weighted, and gas pressurized. The weighted type uses a weight to provide the pressure on the fluid. This has the advantage of providing a constant pressure, but the disadvantage of needing to be mounted in an upright and relatively stable position. The gas pressurized type uses a gas, dry nitrogen, under pressure to provide the push on the fluid. This is the most popular type because the pressure it exerts is easily adjustable and can be mounted in any position. The flow control valve is used to regulate the flow rate of hydraulic fluid. For this discussion, the most important type of flow valve is the directional control valve, which regulates the movement of the piston in the cylinder. A sophisticated device, it must be capable of admitting pressurized fluid to either end of the cylinder while providing a return path for the fluid being squeezed out of the other end of the cylinder. The control valve consists of 2 major parts, the valve body and the spool. You can see that the valve body has 4 fluid connection ports: high pressure fluid supply from the pump, low pressure return to the tank, and 3 and 4 are connections to both ends of the cylinder. The spool is a solid metal machined shaft that can slide back and forth in the valve body. The spool in this illustration has 2 deep grooves that allow fluid to pass from one port in the valve body to another. The position of the spool within the valve body determines how fast and in what direction the piston will move. The spool is moved by a hand lever, an electric actuator such as a solenoid, or a small hydraulic or pneumatic actuator. The following is a description of the operation of the spool type valve shown. To really understand this design, take the time as you read to trace the flow of fluid in each diagram. Figure A shows a valve with a spool centered. In this position, the fluid from the pump is completely blocked by the spool. The lines connected to the cylinder are also blocked, and the cylinder fluid is thus trapped. The piston is locked in place. This explains why a backhoe hydraulic shovel will remain in the upright position even with a heavy load and the power off. However, do not trust your safety to this feature, as hoses can leak. Figure B shows the same valve with the spool moved to the right. Notice that the right-hand groove is allowing the fluid to pass from the pump to the right end of the cylinder, causing the piston to move to the left. The left spool groove has moved into the position to allow an escape route for the fluid being pushed out of the left end of the cylinder. This low pressure fluid is allowed to return to the tank. Figure C shows the same valve with the spool moved to the left of center. Now the high pressure fluid from the pump is allowed to pass via the left groove to the left end of the cylinder, causing the piston to move to the right. The return fluid from the cylinder passes through the right groove and then back to the tank. This is a diagram using standard symbols of a complete simple hydraulic system, which includes the tank, filter, pump, accumulator, pressure control valve, directional control valve, and cylinder. The constant displacement pump would be running all the time the system is on. During those times when the cylinder is not working, the fluid from the pump, after filling the accumulator, returns to the tank through the pressure control valve. Of special importance is the filter that removes small contaminants which get into the fluid. These contaminants can cause abrasive wear on the system components and reduce their lifetime considerably. Of note here is when you use hydraulic systems, keeping the oil clean and dust free is your major endeavor. This was a very superficial look at a hugely interesting and challenging field. It is a topic not often covered by electrical or electronic engineering courses, but could be a lucrative area for mechatronics engineers to cross-train into. Students are encouraged to take up further research in this field.